Here are two more examples of solving equations using the quadratic formula. And in particular, these equations have to be in the standard form quadratic equation. Now we could get sneaky and solve quadratic-like things, but for now, let's go ahead and stick to these ones that I have up here, not get too crazy just yet. So, using the quadratic formula, let me write that down one more time. See if you remember it as I'm writing it. Can you write it down as well? That'll be a fun test. Okay. I'm not going to say it out loud because you're probably writing it right now. Okay, you've got about 2 more seconds. All right, there it is. There is the quadratic formula. And remember, those represent solutions to the quadratic equation. So the first thing I'm going to do is label my A, B's, and C's. A equals 2 in the first example, B equals -3, and C equals -7 related to that formula. Now I'm going to apply the formula. Let's go ahead and plug in everything directly. That's what's so nice about this quadratic formula. So here's what it looks like. -b is -3. So be careful with that, especially if you have a negative for the b term. Plus or minus the root of b squared minus 4ac all over 2a. And don't forget that bar has to go under everything, okay? All right, let's just continue to simplify. So -3, that gives me +3. Plus or minus, let's see what's under the root. It's like seeing what's under the hood or something. Okay, this gives me 9 for -3 quantity squared. -4 times 2 times -7 is going to give me an overall positive 56. And on the bottom, we've got a 4. So let me just continue here. 3 plus or minus root 65 all over 4. And from here, I'm going to try to simplify it more if possible. I'm looking at that 65. What are the factors of 65? Are there any numbers that are factors of 65 that are perfect squares? Because if they are, I can take the root of that perfect square and get a number here on the outside. Please review the roots videos to remember how to, or to review simplifying roots. Now 65, it turns out, is 5 times 13, so neither of those are perfect squares. That's the prime factorization, so we're done right here. We've got both solutions. We're going to say x is equal to 3 plus or minus root 65 all over 4. Okay. And those are 2 exact solutions, one for the plus, one for the minus. And actually, I have written down the approximations here. See if you can get this correct in your calculator. Let me go ahead and take it to the next step where I'm showing 2 solutions. One of them is 3 plus the root of 65 all over 4. And the other one is 3 minus the root of 65 all over 4. And when I crunch these in the calculator or the computer or some kind of computational tool, doing it correctly, I end up with, to the thousandths place, 2.766 for the plus case, and -1.266 for the minus case. So check my work. See if you get these numbers by doing the computation there. And this makes sense. It's nice to have an exact solution. It's nice to use exact solutions if you have to use them for other mathematical procedures. But in the end, if you're trying to engineer something, then you got to get it down to a number with a specified level of precision. And in this case, I specified the thousandths place. Be careful here also with the root of 65. Do not round that and then add the 3 and divide by 4. The more you round in the middle of the computation, the greater your error tends to be at the end. So if you can avoid rounding at all until the very end, do that. That's going to help you in science classes as well. Okay, Let's take a look at this next example and using the, again, quadratic formula. Here, I'll put this one in blue. So let me label my a, b's, and c's first. What is the a? What is the leading coefficient of x squared? Well, if you don't see it, you can say, oh, there's a 1 there, right? 1 times x squared, that is also x squared. Therefore, I can confidently say a is equal to 1, b is equal to 4, c is equal to 7. Now plug that in to the quadratic formula. X equals negative b plus or minus the root of b squared minus 4 times a times c, all of that over 2a. And now we just have to be very careful in simplifying the rest. Okay. So what does this give us? This gives me negative 4 plus or minus the root of 16. Now we've got negative 4 times 1 times 7, which is negative 28. All right. All over 2 times 1 is 2. And then we keep going. You can see from here that we're going to end up with a negative number under the root. So you can say, okay, there are no real solutions to this equation. And that's true. But there are complex solutions involving the imaginary number I. So I'm going to proceed and get the complex answers, the complex solutions. So let us continue. This gives me negative 4 plus or minus the root. 16 minus 28, that's the same as 28 minus 16. So what do we got there? 12. Oh, but I need the negative, right? It's the same as, but with the negative, all over 2. Continue from here. This gives me negative 4 plus and minus. Now I'm going to separate this negative 12 into factors. The first factor I can say is negative 1. Okay, so there's my negative. And then 12 itself, are there any perfect square factors of 12? Sure, 12 can be 4 times 3. Okay, it's also 6 times 2. It's also 12 times 1, but 4 is a perfect square, so that's the one I like. 4 times 3. And all of that is over 2. Now remember, when you have the root of several things that are being multiplied, you can separate this into the root of each one of those factors independently. Looks like this. Root negative 1, root 4, root 3, all over 2. Okay, see how I separated that? Now, this square root of negative 1 is defined as the imaginary unit. So whenever you have a negative under the square root, let's look at this one, negative 12, you can automatically pull that negative out as I. And that's the reason why I showed you over there. Okay, so negative 4 plus or minus, this one is I, times the root of 4 is 2. The root of 3 just remains the root of 3, all over 2. You could make this look a little nicer and call it negative 4 plus or minus 2i root 3, and all of that is over 2. And at this point, I'm noticing that both this negative 4 and the 2 in front of the I root 3 here can be reduced by 2. So one thing you can do is you can separate each of these pieces of the numerator as over the denominator. So it looks like this. We've got negative 4 over 2. And then the plus and minus just goes right there in the middle. 2i root 3 all over 2. 4 over 2 is 2, so that reduces exactly to negative 2 to account for the negative, plus or minus. This 2 right here cancels with this 2 right there. Or you can say 2i root 3 divided by 2 is I root 3. So I got negative 2 plus or minus I root 3 in the end. And those are the two complex solutions to this problem. Negative 2 plus I root 3, and the other solution is negative 2 minus I root 3. Now there is application, I've probably mentioned this before, for the complex numbers. In fact, there's a whole field of math called complex analysis, and it does have a lot of interesting scientific applications. I ask you to look that up and check it out on your own. Stay tuned, and I'll give a couple more examples of using the quadratic formula.